So the next lecture is by Shimon Whiteson. He'll tell us about reinforcement learning, very hot topic nowadays. So please.
Okay, good afternoon, everyone. My name is Shimon Whiteson. I'm from the University of Oxford. It's a pleasure to be here today and to have the chance to tell you about one of my favorite research topics, which is reinforcement learning. I've been given the task of giving you a whirlwind tour of this quite expansive topic in really just a few hours of lectures. So there is a lot of material to cover, and I've had to exclude a lot of topics that in an ideal world I would love to introduce you to, but we'll cover as much of the foundational stuff as possible. My approach to this introduction is to assume basically no background in reinforcement learning. So those of you who have some background in the field may find some of this familiar or even repetitive. But of course I am assuming some background in machine learning. So this is a brief overview of what I hope to cover in the course. Approximately the first half of the course is closely based on the Introduction to Reinforcement Learning textbook by Sutton and Bartow, which there was recently a second edition. You can find this textbook free online, so if you want to read in more detail, I encourage you to do so. About halfway through, it starts to diverge from the book, but nonetheless, you'll find the book to be an invaluable reference if you want to study this field further. So what I hope to cover today in the two lectures that we have today are the most foundational materials, so what we call tabular methods, the Markov decision process, and the value functions, and the basic planning and learning methods. So those of you who are excited about deep reinforcement learning, I'm very sorry, you will have to wait till tomorrow. Once we have that foundation, then tomorrow we can talk about function approximation, which is a key step to making these methods actually scale to interesting problems, and that leads us to deep reinforcement learning. Then on Wednesday, we will talk about policy gradient methods and probably run out of time, but in an optimistic world where we don't run out of time, we will also talk about model-based reinforcement learning. Please don't hesitate to interrupt me at any time if you have questions. If you're behind me, you'll probably have to shout to get my attention. Okay, let's dive right in. So what is reinforcement learning? Reinforcement learning is a subfield of machine learning that tries to answer the question, how can an intelligent agent learn from experience how to make decisions that maximize its utility in the face of uncertainty? So as we go along, hopefully we will get more formal about what we mean by agent, utility, and uncertainty, and we can state the problem more precisely. But at an intuitive level, we have an agent that's interacting with the world, not just passively receiving data and making predictions based on it, but actually out there in the world interacting with it. And it has some notion of utility, some notion of goal, what it wants to achieve. And it has uncertainty about what the world is like, what the effects of its actions will be, and therefore how it ought to act. And in the face of this uncertainty, it needs to engage in some kind of optimal decision making so as to maximize that utility or an expectation over that utility. So here's a highly simplified Venn diagram that tries to position reinforcement learning in the larger field of artificial intelligence. So on the one side, you have knowledge-based systems. This is all the deductive AI, the sort of old-fashioned AI, planning methods, logic-based systems. You give the computer a bunch of facts, and you ask it to make deductions about the world. Then on the other side, we have machine learning, what this whole summer school is about, which is inductive. We just throw a bunch of data at the computer, and we ask it to infer a bunch of rules. So if we think of machine learning as a spectrum, then reinforcement learning is somewhere in the middle of this spectrum. So at one extreme, we have unsupervised learning, where we don't give the computer really any help at all. We just say, here's a pile of data, do some clustering, discover some low-dimensional manifold in the data, whatever. It's just a pile of data. And at the other extreme, we have supervised learning, where every decision that we want the computer to make, we give it a labeled example of the right answer. So the data consists of not just x's, but xy pairs. So we have a strong form of feedback. Reinforcement learning is in between these two extremes because unlike unsupervised learning, we do have meaningful feedback, and that meaningful feedback comes in the form of a reward signal. But this reward signal is fundamentally weaker than the feedback we get in supervised learning, because in reinforcement learning, the agent that has to learn is never ever told what the right answer is in any situation. Whereas in supervised learning, at least for the training set, you are told what the right answer is. So instead, this reinforcement learning agent just gets positive and negative reward for the actions that it tries, but it never knows, even if it gets a positive reward, if there might not be some other action out there that would get 1,000,000 times as much reward. So this is useful but weak feedback. Okay, so reinforcement learning, as I already hinted at, is about an agent that's using data to try to learn to solve a control problem by interacting with an initially unfamiliar environment. So in the extreme case, you can think about like a rover dropped down on Mars, and when the rover lands on Mars, it doesn't know what the laws of physics are, it doesn't know what its goal is, so through trial and error, it has to take actions, see what their effects are, figure out which sequences of actions will get it the most reward. This is learning by trial and error. Obviously, this is applicable to robot control. In addition, game playing, both in the sense of board games, but also in the sense of video games. These are some of the most successful application areas of reinforcement learning. Also some less glamorous but extremely practically important areas like system optimization. You have some network of thousands of computers. You want to optimize the flow of data between the computers, or the balancing of load, the balancing of jobs as they're assigned to different machines in the system, that sort of thing. Ad serving and information retrieval, so deciding how to respond to requests to users with information that might help them or ads that they might be interested in. These can be modeled using reinforcement learning. One thing I like about reinforcement learning is that, like many other areas of artificial intelligence, it's a naturally interdisciplinary field. So the reinforcement learning model is actually borrowed from behavioral psychology. It's related to some areas in engineering, like operations research and control theory. It can be thought of as a sort of data-driven machine learning variant of other areas of AI, like classical planning methods. And it even connects back to neuroscience. So the reinforcement learning model was borrowed from behavioral psychology, but then has been taken back sort of to the other side of the fence and used by neuroscientists to understand how the human brain works. Probably the best way to understand reinforcement learning for people like you who already know something about machine learning is to contrast it with supervised learning. So there are three key differences. One of them I already mentioned, and that's that unlike in supervised learning, a reinforcement learning agent never gets examples of correct or incorrect behavior. It just gets these rewards that could be positive or negative and has to figure out how to maximize those rewards. So that's one key difference. The second key difference, the agent is active in the learning process. So what that means is that the agent has partial control over the data it will obtain for learning. So we can contrast this again with a typical supervised learning setting where you have some fixed data set, you throw the data at the computer cranks away at it, and then outputs some hopefully useful learned model. So in that setting, the computer had no control over what data it got to train from. The data it just passively receives and operates on the data. Whereas in reinforcement learning, the actions that the agent takes while interacting with this world will affect what data it collects in the future. So if I go over here and look around, then I'll get a different sensory readings than if I go over here and look around. So this is a fundamental complication in the learning problem, because the agent has to reason not just about what actions will get it reward, but what actions will get it the data it needs to learn better in the future. It's a complication that doesn't arise in the standard supervised learning setting. And the third key distinction is that the agent is learning online. So when we say this is learning through trial and error by interacting with an unfamiliar environment, this environment is not a game. This environment is the real world. So the actions that we try, they have real world consequences. If the agent has an action and that action triggers a negative reward, that negative reward, this is not monopoly money. This is real, this corresponds to real world costs as a result of taking that action out in the world. So what this means is again, unlike in a traditional supervised learning setting where, you feed this data to the computer, it cranks away for a while, and, you hope that that cranking doesn't take too long. You'd like for it to learn quickly. But really all you care about is the quality of the model that comes out at the end of the learning process. That's not true at all in reinforcement learning. So it's not good enough at the end of the day to find a good policy, a good solution to the reinforcement learning problem. We have to maximize the reward we accrue during the learning process. And this again leads to fundamental challenges that don't arise in a canonical supervised learning setting. Yeah? Yeah, so that's a very good question. So if we look at this list of 3 distinctions that I made, actually only the first one is completely universal to the concept of reinforcement learning. So there's a canonical reinforcement learning setting, and then there are many variants of it. And those variants might violate these second and third bullets. So you can also do reinforcement learning offline from data that was collected in advance, and you have no control over that data. And you can also do reinforcement learning by interacting with a safe simulator or in a safe laboratory where the negative rewards don't actually correspond to real-world costs. Now, we can argue about terminology if I want to be really specific about the difference between planning, which is deductive, and learning, which is inductive. I might argue that if you're doing reinforcement learning by interacting with a simulator, what you're actually just doing is a sample-based planning, and it's not strictly speaking reinforcement learning. But of course, people commonly refer that to reinforcement learning, and I don't want to be too nitpicky about terminology. But the sort of canonical reinforcement learning setting is interacting with the real world in order to try to maximize reward. Good question. Okay, so the reinforcement learning framework, for better or worse, is extremely general. And the more you study reinforcement learning, the more it starts to seem like the entire world is a reinforcement learning problem. And this is a perspective which has actually been formalized by Rich Sutton, who quite literally wrote the book on reinforcement learning, in what is sometimes called the reward hypothesis, which says all of what we mean by goals and purposes can be well thought of as maximization of the expected value of the cumulative sum of a received scalar signal, the reward. There are many, many objections that one can raise to the reward hypothesis. So there are many situations where we might not want to maximize expected value, but we might want to be risk sensitive. So we might be risk seeking or risk averse and care about some other metric other than expected value. Or we may care about some notion of value which doesn't decompose as a sum of instantaneous reward signals. Or we may have multiple objectives, so the reward that we want to optimize is actually a vector and not a scalar. But what I want to emphasize here is possibly the most significant aspect of the reward hypothesis is it really codifies the key restrictive assumption of the reinforcement learning setting. So while it is extremely general, it does rest on one key assumption, and that assumption is the existence of this reward. So the agent can arrive on Mars with no prior knowledge about how the world works or what its goals are, but nonetheless, a mechanism must be in place such that when it takes an action, it receives a sample reward. So someone, somewhere, must have defined this reward function, and the goal of the agent must be quantifiable. We must be able to write it down in the form of this scalar reward function. Otherwise, reinforcement learning is inapplicable. So this limitation gives rise to what is sometimes called the reward design problem. So the reward design problem is the difficulty faced by the human engineer who has to perform this quantification, who has to say, what do we mean by reward? What is the definition of good and bad actions for this agent? And this may seem trivial in a task like, playing a board game or playing chess or something. It is trivial. But in many real-world tasks, what you actually want the agent to do is surprisingly tricky to quantify in the form of a reward function. So this is the reward design problem. So this is, I want to show a short video. So this is my favorite example of the reward design problem. So my colleague David Ha, who's at Google Brain, posted this video on Twitter. So he was trying to train a simulated humanoid robot to walk as far as possible. So he gave it a reward function where every meter it traveled, it got a point. A very sensible definition of the reward function. So here's what the learned behavior looked like. Oh, sorry, it's not the beginning of the video. Here we go. Okay, it goes on like that. Okay, so the key thing to realize here is that this is actually not a failed policy. This is a fantastically successful policy because it maximizes the reward function that was given to the agent. And yet, the learned behavior is not at all what we wanted. So this illustrates the difficulty of the reward design problem. Right, so this is the last point in this series of lectures in which I'm going to talk about the reward design problem. If you have a real-world setting where reward design is difficult, there are other techniques you might consider. So, for example, learning from demonstration, where you learn to imitate an expert instead of to maximize a reward function, that will not be covered here at all. So in everything that follows, we assume that we are able to correctly formulate the goal in the form of a reward function. And everything follows from that. So this is just a warning to the user. Make sure you have the right reward function before you apply reinforcement learning. And if you aren't confident in your ability to define the reward function, think about maybe using another technique. Okay, so what I want to do now is start from an extremely simple model and build to the full reinforcement learning problem. So the starting point is the K-armed bandit problem, which some of you may or may not be familiar with. Actually, can I see a show of hands? How many people are familiar with the K-armed bandit problem? Okay, it looks like about 50%. Okay, so I just have a few slides of background about this. The K-armed bandit problem is one of the most studied problems in theoretical machine learning. And it's a nice problem because it captures not all, but one of the key challenges of reinforcement learning. So it's good for isolating this key challenge, and then once we wrap our heads around this model, we can build to the more complex, full reinforcement learning problem. Okay, so the K-armed bandit problem works as follows. You are this octopus, and you're at the casino faced with a row of slot machines. Every one of these slot machines is governed by an unknown stochastic payoff. So there's a random variable associated with each arm, and you don't know the law that governs that random variable. And at every time step, you can select one and only one of these arms. And your goal is to maximize your cumulative payoff over some period of time. So formally speaking, we have K actions available at each time step. These are sometimes called plays or pulls. And every time we take an action, we receive a reward that is sampled from the random variable that governs that arm. And now we can formulate our goal in two different ways. In the finite horizon problem, the agent tries to maximize the total amount of reward it receives after some finite number of steps. So you can think of this as like, we know in advance that the casino closes at 5 p.m. We want to leave the casino with as much money as possible. Okay. Of course, many real-world problems don't work this way. So for example, if you're Google and you're trying to optimize your search engine by formulating it as a K-armed bandit problem, you're going to have trouble defining this horizon. What is this capital T? Because you'd like your search engine to run indefinitely, or at least as long as search is a useful technology, which even if that's not forever, the time at which it will end is unknown to you. So this can be more usefully modeled as an infinite horizon problem, which is exactly the same, except that this summation becomes an infinite summation. And then to ensure a finite result, the rewards are weighted by this discount factor. So here we have this parameter gamma, which is raised to an ever larger power, and which downweights future reward based on how far in the future it is. So if we set gamma to 1, then that means we care about future reward just as much as we care about the reward we get now. If we set gamma to 0, all we care about is immediate reward. We don't care about the future at all. So we can interpret this in a few different ways. So one interpretation is an economic interpretation. it's better to have money now than to have money later, which is why when you borrow money from the bank, you have to pay it back with interest. So, the degree to which it's better to have money now rather than later is quantified by this gamma parameter. Or we can interpret it probabilistically. We can imagine, suppose we are actually in a world where the game will end, but we don't know in advance when it's going to end. And at every time step, there's a 1 minus gamma probability of the game ending. Then what we're doing in this infinite summation is we're just weighting future rewards by the probability that the game lasts long enough to actually get that reward. Okay, so the fundamental challenge of the K-armed bandit problem is the exploration-exploitation dilemma. So in order to get reward, we're going to have to learn about the arms. We need to figure out what are the good arms and what are the bad arms. That means we have to explore. The only way to learn about them is to try them out. So we're going to have to try out a lot of different arms to figure out what the good ones are. But remember, we're learning online. So it's no good if we leave the casino at 5 p.m. and say, hey, I found out what the best arm is, but I don't have any money. That's useless. All that matters is how much money you have in your pockets when you leave the casino. So before time runs out, you need to use what you've learned about the arms to exploit, to focus your energy on the most promising arms and get the most reward. Right, so this is the main challenge of the K-armed bandit problem. Before we talk algorithmically about how to approach it, first a few simple observations. So first of all, if the horizon is finite, exploration should decrease as the horizon gets closer. Hopefully this is intuitive. In the extreme case, at the last time step, there is no future, so there's no point in exploration. So we can think of exploration as a means to an end. The point of exploring is to learn something so that later when you will exploit better. If there is no later, because the world is about to end, there's no point exploring. You might as well just exploit based on what you already know. Okay, observation 2. If the horizon is infinite, but gamma is strictly less than 1, then exploration should decrease as the agent's uncertainty about the expected rewards goes down. So hopefully this is also intuitive. If you've pulled an arm once, when you pull it the second time, you get a lot more information about that arm. If you've pulled the arm 1,000,000 times, then pulling it that 1,000,000th first time won't give you a lot more information. So there are diminishing returns here that make exploration less attractive as your uncertainty goes down. So as our uncertainty goes down, we should shift more and more to exploitation. And then finally, if the horizon is infinite and gamma is equal to 1, which I said wasn't allowed, then you get a phenomenon called the infinitely delayed splurge. So what this means is, no matter how many times you've pulled the arms, you always have some non-zero amount of uncertainty. There's always some probability, no matter how infinitesimal, that everything you've seen so far was a statistical fluke and the world actually looks totally different than your estimates. As long as that possibility exists, if gamma equals 1, you have an infinite future ahead of you. So you always are interested in delaying exploitation. You say, okay, I could exploit now and I'd get a big payoff, but I could also explore and further reduce that infinitesimal uncertainty so that later when I exploit it will be even better. And that same reasoning applies at every time step, so you constantly delay exploitation and you never actually get around to it. So this is one reason why we typically want gamma to be strictly less than 1, so we have a model that actually exploits at some point. Okay, now the very simple idea underlying basically all bandit methods is the idea of an action value function. So if in your head you were already thinking about an algorithm to solve the K-armed bandit problem, I promise you implicitly it was an action value method. So the idea is very simple. Based on the rewards that we have observed, we're going to estimate the expected payoff of each arm. This is called a Q value. And these estimates are just constructed from a sample average. Now, given these estimates, we can formalize what we mean by exploitation. So exploitation means taking the greedy action, the action which appears to be best according to our Q values, which crucially may not actually be the best action because our Q values are just estimates. And exploring means doing anything else. The only reason not to take the greedy action is to learn something that might help you take better greedy actions in the future. Okay, so let's look at a few simple K-armed bandit algorithms. First, the absolutely most naive thing to do is called epsilon greedy exploration. So you can understand it from this diagram. So on the x-axis, I've sorted the available actions according to their current Q value. And on the y-axis, we have the probability of selecting that action according to the epsilon greedy rule. So most of the probability mass is reserved for the greedy action, so that's exploitation. And the rest of the probability mass is uniformly distributed on the other actions in order to assure sufficient expiration. This is an extremely naive algorithm, but one nice property of it is that in the limit, it will converge to the best arm. So because we never starve any arm, every arm has some probability of being selected. If we're wrong about what the best arm is, we will eventually discover what the true best arm is, because the law of large numbers will ensure that our estimates become correct in the long run. Okay, one of the many limitations of this algorithm is that when it explores uniformly. So one step better is called softmax expiration, where we assign these probabilities according to a Boltzmann distribution. So again, it's easiest to understand from the picture. As before, the most probability mass goes to the greedy arm, but now the second best arm gets a lot more probability mass than the worst arm. So we concentrate our expiration on the most promising arms. So neither of those methods take into account our uncertainty. And remember, one of our key observations about expiration and exploitation was that our decision-making should be conditioned on our uncertainty. So in order to do this, we can use what's called the principle of optimism in the face of uncertainty. So we can quantify our uncertainty about how good the arms are, and then we can use that to build an optimistic interpretation of the world, and then we can act greedily in that optimistic world, resulting in exploratory behavior. So this leads to perhaps the most famous K-armed bandit algorithm called upper confidence bound. So again, this is easiest to understand from the figure. So on the x-axis, we have the actions again, but now in arbitrary order. And on the y-axis, we have not only their q value, but a confidence interval that we construct around that q value. So the upper confidence bound algorithm algorithmically is extremely simple. At every time step, it selects the arm with the largest upper confidence bound. So in this case, it will select this arm. So intuitively, there are two ways that an arm can have the highest upper confidence bound. The first one is by having a high mean, in which case, regardless how big that confidence interval is, the upper confidence bound will be large. And this would result in exploitation. We select in the arm because it has a high mean. We expect a large payoff. Or you could have a high upper confidence bound because the confidence interval is large. Then even if your mean is kind of low, if the uncertainty is big enough, the upper confidence bound will be large enough. So this would be exploration, focused on arms that are sort of promising but uncertain. So this is formalized here in these equations. So we're going to select the arm that maximizes this upper confidence bound, which is just the sum of our q value and an optimism bonus, which you can think of as 1/2 of the confidence interval. And this optimism bonus is defined according to this rule, which can be derived from a concentration inequality called the Hufting bound. But intuitively, in the denominator, we have a term which grows with the number of times we've pulled the arm. So again, intuitively, if I've pulled the arm 1,000,000 times, my optimism bonus should be smaller than if I've pulled the arm only once. And in the numerator, we have a term which grows with time regardless of whether we pull the arm, but it grows only logarithmically. So this means that I am forced to keep rechecking my decision that some arms are suboptimal. So suppose some arm is suboptimal, and I'm ignoring it, I'm starving it. While I'm starving it, its confidence interval is going to grow over time because of this numerator, until eventually that confidence interval gets so big it pops back up to the top, and I'm forced to pull that arm again, and then either reconfirm my conclusion that it wasn't a good arm, or discover, hey, this arm is more promising than I thought, let's continue to investigate it. Okay, so that was a whirlwind tour of the K-armed bandit problem. So what I want to do now is take one baby step towards the full reinforcement learning problem by stepping to an intermediate problem called the contextual bandit problem. So in some of the older literature, this is also called associative search. So it's just like the contextual bandit, just like the bandit problem, but at every time step, before the agent has to select an action, it receives some side information, an observation, a state signal. And the expected payoff of each arm depends on that observation. So before acting, you get that observation, and the right thing to do depends on what you've observed. So one way to think about this is, imagine you're at the casino and there's not just one row of slot machines, there are many rows of slot machines. And each of them is painted a different color. And before you have to pull an arm, you get to see what the color of the row of slot machines is that you're currently at. And once you pull that arm, you're sort of transported randomly to another row of slot machines. And you have no control over where you'll end up, but wherever you end up, you'll get to see the color before you have to decide. So, in principle, we can just think of this as multiple simultaneous bandit problems, and we can use the same tricks that we were doing before. It just, instead of having these Q values that condition on the action, we have these Q values that condition on state-action pairs. So how good we think an action is going to depend not just on what action it is, but also what state we're in, what color we observed before we acted. Of course, this problem becomes more interesting when we have a large number of states or continuous state space, so that we have to do some generalization across these bandits. But conceptually, it's just like a bandit problem, but with this complication of this extra state information. And this problem is not just of theoretical interest. People in industry are extremely interested in K-armed bandit problems, and in particular the contextual bandit variant of it, because if you can solve that problem 0.1% better, that literally means millions of dollars or pounds or rubles or whatever currency you prefer. So like imagine you're Google and you have this AdSense program where you pay people to place your ads on their website. So now you have to decide what ads to show a user so that they're most likely to click on the ad. If they click on the ad, you get paid. So we can think of the web page as the state, the web page and maybe whatever we know about the profile of the user. And the actions are all the different ads that we could choose from. So the environment that we interact with is then the user that decides to click or not click, and if we get a click, then that's a reward function. So we want to figure out how to maximize this reward function by showing the ads to a user or on a web page that are most likely to generate a click. So there's a lot of big money involved in doing this better. Okay, so that was the first baby step. The second baby step brings us to the full reinforcement learning problem. So in the full reinforcement learning problem, we just have one additional complication we didn't have in the contextual bandit problem, and that is that our actions have broader effects. So in the K-armed bandit problem, we take an action, it triggers a reward, some coins come out of the slot machine, the consequences of that action end there. If it was a contextual bandit problem, after we receive those coins, we're teleported to another row of slot machines of a different color, but we have no control over how that teleportation plays out. In the full reinforcement learning problem, we do have that control. So our actions affect not just our immediate reward, but they also affect what state we're in next. And this makes the model much more realistic, because if you want to think about any interesting problem like where a robot is out there moving around in the world, obviously the actions that it takes don't just affect its reward, they affect the state of the world. Even if the only effect that they have is the position of the robot in the world, the robot's position is part of the state. So in almost any interesting problem, your actions affect the state, not just the reward. And that's what's modeled in the full reinforcement learning problem. And this is a significant complication because it's going to require much more complex reasoning to figure out the right way to act in a world in which our actions affect the state of the world and not just the reward that we get. In particular, the main complication is the credit assignment problem. So, imagine you have an agent that plays chess, and it takes a long sequence of actions. After 72 moves, it wins the game, it defeats the opponent, checkmate. Now you have to go back and look at this sequence of moves, and for any individual move, you look at move 17 and say, okay, how much credit does this move get for the ultimate victory in this game of chess? Maybe this was the critical move that decided the whole game. Everything else was unimportant. This was the move where you won the game. Or it could be the opposite. Maybe this move was actually a catastrophic blunder, but you played so well after that that you managed to win the game anyway. How do you tease that apart? That's the credit assignment problem. And that's a complication that doesn't arise in the K-armed bandit problem because the credit assignment is trivial. If you receive a reward, you know it was due solely to the action that you just took. So credit assignment is trivial there. So tackling the credit assignment problem is the main additional challenge we'll have in the full reinforcement learning problem. And the principled solution to the credit assignment problem is due to Richard Bellman, who can be thought of as the father of decision theoretic planning and possibly the grandfather of reinforcement learning, because Bellman came up with decision theoretic planning, the Markov decision process, the Bellman equation, the dynamic programming, all the things I will talk about shortly, which is the foundation on which reinforcement learning was later built. So we can think of reinforcement learning as machine learning, data-driven variants of the foundational concepts that were developed by Richard Bellman. So the IEEE has called him a towering figure among the contributors to modern control theory and systems analysis. And my colleague Brambacher once said, the Bellman equation is one of the 5 most important ideas in artificial intelligence, which I thought nicely encapsulated the significance of his body of work. Don't ask me what the other 4 are. I have no idea. And he did all this work back in the 1950s, so in this picture you see what's behind him is a computer. The computer did not have a screen. He's looking at the printout from that computer. So this was, really, really early days, really seminal work, which remains extremely significant and influential even today. How am I doing on time? I'm supposed to stop at 1:30, is that right? I think so. Okay. So Bellman's work starts with the Markov decision process, and the Markov decision process formalizes this full reinforcement learning problem that I was describing. So it formalizes this additional step beyond the contextual bandit problem. Okay, so it's an environment in which we assume the agent can fully observe the state of the world. We'll talk a little bit later about what that means. It's a stationary world, so that means, the state of the world may be changing and the information state of the agent may be changing, but the laws of physics are not changing. The rules that govern how the world changes in response to actions is fixed, so it's stationary in that sense. But it's possibly stochastic in the sense that, there are some dice rolls involved. When you take an action, it may not be deterministic what next state you arrive in or what reward you receive. Okay, and it consists of the following components. So we assume discrete time. Now, in the simple methods that we will talk about first, we will also assume discrete states and actions. Though later we'll talk about methods that deal with continuous states and actions, but we will always be talking about discrete time. So we have a set of discrete time steps, and for now, a discrete set of possible states that the world can be in, a discrete set of actions that the agent can take, and the set of actions available to the agent may be different for each state. And then crucially, now we have this transition function, and this transition function tells us the probability of arriving in some new state given the current state and the action that we took. And again, so these are probability distributions, so this is a potentially stochastic world. And then we have a reward function which tells us the expected immediate payoff that we'll receive if we take an action in a certain state and arrive at the next state. So if you look at the literature, you'll see some variations on how the reward function is defined. Sometimes it's defined only as a function of the current state and action, not the next state, sometimes even a function only of the current state. This is the most general formulation in which it depends on the current and the next state as well as your action. All these variants can be converted from one to the other, so the difference is not very important, but just so you are aware. And then again, just like in the bandit problem, we can have a finite planning horizon, or we can have an infinite formulation where we have gamma that is strictly less than 1. So here's a nice example from the Sutton and Bartow book of a simple Markov decision process. We have this robot, and it has a battery which can be in 2 different states, the high state or the low state. And it has actions available to it. It can either go search for cans it needs to collect, or it can wait. And in the low state, it also has the option to go back to its base and recharge. And then this diagram shows basically how the transition and reward functions work. So if you're in the high state and you decide to act, then you might transition to the low state. If you decide to wait, then you will stay in the high state, and the different actions will generate different rewards. So I wouldn't spend too much time on the details there, but this is just a simple example of a Markov decision process. The reason it's called the Markov decision process is because this assumption that that the world is fully observable is formalized using the Markov property. So we can say the agent can see the true state of the world, but what do we mean by that? What is the true state? So the true state is some information given to the agent which satisfies the Markov property. And the Markov property says that our ability to predict the next state and the next reward, conditioned only on the current state and current action, is the same as our ability to predict the next state and reward given our entire history. So in other words, the future is conditionally independent of the past given the present. This is the Markov property. So the current state is a sufficient statistic for the agent's whole history. If I know the current state, I can safely ignore the history without losing any ability to predict the future. And this is a crucial property because it means conditioning agents on the history cannot possibly help. And when we later get to algorithms for reasoning about a Markov decision process, we can restrict those algorithms to ones that consider reactive policies. And a reactive policy is a policy that selects an action based only on the current state. So for every state, it will specify a probability distribution over actions. Or in the deterministic special case, it will just supply a direct mapping from states to actions. And we can do this because of the Markov property. We know that conditioning on the history wouldn't help us. So in every Markov decision process, there exists at least one optimal deterministic reactive policy. So we will consider stochastic policies for various reasons that become apparent later, but there will always exist at least one deterministic one that crucially is reactive, meaning it conditions only on the current state. So we started a few minutes late, so I was told to go to 1:30. Is that okay? Yeah. Cool. We will stop in the next 8 minutes. Okay, so let's play a little game called Is It Markov? So imagine you're a robot in a maze, and your state is an observation that tells you on all 4 sides of you whether there's a wall or no wall. And the actions available to you are to move in the 4 cardinal directions, up, down, left, or right, unless there's a wall in the way, in which case you can't move. So is it Markov? Does anyone want to venture? Why not? Yeah, exactly. So a simple example is if you look at a hallway here. While I'm in this hallway, all the observations look the same. But if I'm at the end of the hallway, then my next observation looks different. So if I can remember by looking at my history how far down the hallway I am, I can make better predictions about what I will observe at the next time step. Am I going to see another bit of hallway, or am I going to see a corner? So this is not Markov. Okay, let's suppose we're playing chess, and the state that we are given is the current position of the board, but not the history of moves, just the current position of the board. And the actions available to us are all the legal moves of chess. And our opponent has a fixed reactive policy. So I'm not trying to get into a multi-agent minimax game theory thing here. The other player is just part of the world and is acting according to a fixed policy. So we can still think of this as a single agent decision-making problem. Is it Markov? Yeah? Yes. Okay, well, do you want to argue why? So that is absolutely the right idea and the correct intuition, but it is the wrong answer because this is kind of a trick question.
There's like 50 move rules, or if you do repetitive moves, then we get to one. And so that is also an outcome when we want to signal that it's dependent on the history.
Yeah, exactly. So in chess, there are some special cases like you can castle, but you can only do it once, and if you come to the same board state too many times, then it's a stalemate, and so on. I'm not a chess player, so I don't know all these rules, but there are some special cases like that make it non-Markov. But the intuition, if we were to throw away all those special rules, your intuition is exactly right, which is that if you know the board position, you don't need to know the history, because all that matters is what board position that history brought you to. Okay, I think this is, well, I guess I have 5 minutes, so let's do a couple more slides before lunch. Okay, so in order to reason about the credit assignment problem, we're going to have to reason about the long-term consequences of our action. So unlike in the bandit problem where we could say, I took this action, I got this reward, and that's the end of the consequences of the action. Now, if you take an action, it brings you to a different state, which will then affect what actions you can take in the future and what your opportunities for reward are long-term. So the consequences of an action can be quite persistent. So that means we're going to need to reason about long-term consequences. And we can do that using this notion of a return. So the goal of the agent in this full reinforcement learning problem is not to maximize its immediate reward, but to maximize its return, the expected return, where the return is just a sum over the rewards received. Okay, so the return is just a sequence of rewards summed up and weighted according to the discount factor. So it's a discounted sum of the rewards that we receive. Right, so we can define this sum for both the finite and the infinite horizon setting, and there are ways to write one formalism in terms of the other, but I think I will skip that because it's not very important. So we just focus on the infinite horizon setting for now on. Okay, now all of the solution methods that Bellman invented are based on the notion of a value function. And a value function is just a conditional expectation over return. So the simplest form of this is the state value function. So the state value function says, now it conditions on two things here. We condition on the current state, and we condition on the policy that we're using. Remember, the policy was a mapping from states to actions, or a mapping from states to probability distributions over actions. So given that we've committed to using this policy, and that we're in some particular state, what is the expected return? So this capital RT is the return, which remember is just this discounted sum of rewards. Okay? And for reasons that will become clear later, it will also be useful to reason about action value functions, which are the same idea, but now we condition not just on the state, but also on the current action. So what this means is, if I'm in this current state, and I take this action A, and thereafter I follow policy pi, what is my expected return? And the crucial thing to understand here is that this action A may not be the action which was recommended by policy pi. So the Q function tells us the expected return if we take some action now, ignoring the policy, and only thereafter follow the policy, what is our expected return? So this will help us reason about one-step deviations from the policy, which will be crucial to optimizing policies later. Let's see. I propose we stop here and we do the rest. I think a few hours later, I have another hour and a half to finish off this introduction to reinforcement learning. So I'll see you guys later on. Thank you.